Now we are going to proceed to find the link budget for receiving a TV program from a satellite, from a GEO satellite. We know about the satellite data and also the receiving antenna, and this is how a typical receiving antenna for this purpose looks like. It's placed on the campus of UPC and is pointing south-southeast, as here you have described. And this type of reflector is just a parabolic reflector, but it's a very peculiar shape. It's an offset reflector. Just briefly to comment on this. If you have a symmetric parabolic reflector, then you feed it on the axis with an antenna that will send the wave to the reflector, and the reflector will just bring back the signal to space in a very thin beam. Now, there's some blocking that in those small antennas you have to avoid. And one way to do this is just, instead of using a symmetric reflector, just take another part of the parabola, the parabolic reflector. And it's not symmetric, it's asymmetric. That's why we say it's offset. And now the feed has to be pointing to this part of the reflector. So it sends the wave to the reflector, and then the reflector sends the wave back to space in a different direction, up to the space. So if you look at the reflector has an elliptic shape, although the beam is circular, is symmetric. And this particular reflector has a diameter of 65 centimeters. It's a small reflector, it's a typical. But at this frequency of 11.5 gigahertz, the gain is 36 dBs. We are taking some numbers for the receiver. Let's assume that the noise temperature is around 100 Kelvin. It could be lower depending on the environment, depending on the sun and the atmospheric conditions, but let's take a typical value of 100 Kelvin. And this reflector has in focus, here it has a small horn antenna, and it already has here a low noise amplifier that is normally described as an LNB. And here they are going to just perform and frequency shifting and bring the frequency, the received frequency from the satellite to the first intermediate frequency. Now, in this process, there's a lot of gain here, but there's also some added noise. I'm taking a noise figure of 1 dB, although the nominal value you may see in those receivers could be 0.3, 0.4 dBs, but let's take just 1 dB to make things simpler in the calculation. To complete the picture, we also need to know where we are and what are the weather conditions. The most important factor that may affect the reception is rain. And for this, you need to have some information on two things: where you are, the kind of climatic zone you are, and the ITU has classified them. In our case, is the K zone, and in this report you can have information on this. And the second term that is important is to know if you want, how often in a year this rain is present, that attenuation is present. And depending on the availability, then you will have to pay a larger penalty. For instance, if you assume 99.9% of the time everything should be, the signal should be correctly received, that means about 1 in 1,000, that means about 10 hours per year. Then you don't exceed a certain amount of rain, and for this purpose you have to just define or use a margin of 2.5 dBs. If you want to tie this number, then you will have to increase this number. Depending on your specification, this could be changed, but that's the order of magnitude. Now, with this, we can now work the downlink budget from the satellite to the receiver. We start with the power of the transponder, the gain of the antenna on board the satellite, and this is the basic data. Let's assume it's 54 dB watts. Could be a little bit different depending on where you are, if you are in the center of the beam or you are just close to the edge of the antenna beam. But let's take a typical value, which is the reasonable one for this case. This is the frequency, this is the range, the distance from Barcelona to the satellite, and this is the free space path loss. It's 205 dBs. It's a very large penalty, but that's because of the long distance to the satellite. This gives you a power density at the receiving antenna of 13 picowatts per square meter. So it's a very low level of power. And now we have to add some margins. Here you have some typical ones. Those numbers could be a little bit different, but that's the correct order of magnitude. We don't have much atmospheric losses, but still there are some present. We have to account for possible attenuation by rain. We are not considering ice, snow, or some other cases. Then there could be some polarization mismatch depending on the antenna. There could be some errors in the pointing, but those are not very small values, so all those add to almost 4 dBs. That's the margin we take. So at the end, the total space loss, counting both the free space plus the margin, is 209, maybe 210 dBs. That's the typical value you have to take care of. Now we move to the receiving end. The antenna gain is 37 dBs. We just consider the 1 dB noise figure, and we also assume, in this case, the antenna temperature, noise antenna temperature of 100 Kelvin. With this, we can work and find the noise power, and here we have the received power. So those are the two main lines. You compare the signal, and here, or the carrier, and here you have the noise. And this gives you, with those numbers, your carrier to noise ratio, which is about 14 dBs. That means that your signal is 14 dBs above the noise level. This program we are talking about, we are considering, we are studying, is broadcast following the DBB standard. It's an MPEG-4 program with a modulation of 8 levels, a phase shift keying, and it has a code rate of 2/3. That means for every 2 information bits, we add 1 check bit, a redundant bit. And the symbol rate is 22 megavolts. That's the data or the symbol rate. And the associated data rate, the useful data rate is double of this number, is 42 megabits per second. For this modulation and this code rate, the minimum signal to noise ratio to require is 6.6 dBs, which is well below your margin. So with this small antenna, you can be very confident that you can receive the signal from the satellite without having really difficulties. And that's why with those kind of receivers and antennas, you can have at home a very good quality TV signal with an antenna that is really often small size. The standards are always in change, they are always being improved, because the technology always helps. Now you can do things in a better way. You can have more efficient coders and encoders. You could also have more complicated modulation schemes. You can keep adding things. So now there has been recently used an upgrade, a small change in the standard, and today they are still using this number to indicate that there has been some changes. And you can go to this website and you can get there information on how this standard is evolving. And it's going in two ways. One is just to improve the spectral efficiency. That means having much more complicated modulation schemes and different code rates. So at the end, look, they are saying that you could receive, under very poor conditions, still an acceptable signal, or that you can go to very highly demanding professional applications with a very high signal-to-noise ratio. So those are the two ends of this process. And also, since the coding standards are evolving continuously, and we already have work on a successor to MPEG-4, which is called at this time high-efficiency video coding. Also, they are defining a standard that is going to be compatible with this one in such a way that television signals could evolve towards not only high definition, but also what is normally called ultra high definition, has different names to keep going on afterwards. And this concludes the study of satellite broadcasting cases. And let me just finish by acknowledging the professors that have been involved in this course, preparing this course, and the recording of this video at the facilities of the Universidad Politécnica de Valencia.